And the next, chapter 4, about antifungal features and the properties of chitosan underwood essential oil pickering emulsion coating stabilized by appropriate cellulose nanofiber dosage for fresh fruit application. And this chapter could be accessed freely in scientific reports journal. The objectives of this research are to develop an emulsified coating film formulation based on chitosan and essential oil using Pickering emulsion approach with an appropriate level of cellulose as a stabilizer. And to study the antifungal features against both Triticinaria and Penicillium digitatum and film properties. The various concentration of cellulose nanofiber was used in this research, ranging from 0 until 0.31% of cellulose nanofiber with length in micrometer scale and width about 24.86 nanometers, which was characterized by using AFM that is used to produce Pickering emulsion solution. And then the emulsion containing 0.25% surfactant twin 80 was used as a positive control. As in this figure, a preliminary test was performed to select the optimum dosage of cellulose. It was divided to be 4 groups. For the first group, it exhibited a creaming index of the emulsion in the absence of cellulose. And then the second group, the emulsion was not stable and clearly split into 2 different phases. And group 3 demonstrating the absence of creaming index, which was the same as the group 4, which was a regular emulsion. And the morphology and droplet size of oil was investigated by using CLSM, and its results suggested that the incorporation of 0.24% of cellulose nanofiber may be an ideal stabilizer candidate. And to further understand the structure of Pickering emulsion, the acridine orange fluorescence dye was used. The orange circles around the spherical droplets indicated that the stained cellulose lay on the surface of the dispersed paste. As expected, in vitro analysis showed that the coating restricted the growth of fungi compared with the untreated or control and alginate representing the commercial edible coating. And there was no significant difference when the cellulose was loaded. There are 2 proposed mechanisms. First, in the study, the use of cellulose was at appropriate concentration as a Pickering agent without reducing antifungal and without reducing the antifungal features of chitosan essential oil composite. And then cellulose maybe inhibit the loss of essential oil due to the environment exposure. It was confirmed by membrane integrity test with the aid of propidium iodide fluorescent dye. The coherent result was obtained from in vivo test using tangerine and apple. Again, there was clear evidence of appropriate level of cellulose as a stabilizer and the improvement of antifungal action. And there was surprising findings that the pH value in the last day of storage lower than the 4 days. This might be ascribed to the availability of intrinsic carbons of fruits. On the final storage, the higher number of carbon source may be available in the coated fruits, while the molds or fungi have already exceeded the lag pace or adaptation pace in the host environment. And this Ketosan film also had the highest clarity compared to the essential oil-loaded Ketosan. It has a lower transmittance, and moreover, there were sweating out of the oil indicated by the yellow arrow from the inside to the surface of the film with the naked eye due to the drying process. And the highest reduction in the light transmission was demonstrated with the Pickering emulsion film. It's likely that ketose nanofiber, cellulose nanofiber addition affected the internal and the surface structure and efficiently blocked the UV and visible spectrum of light. And the use of cellulose as a Pickering emulsion again increased the tensile strength. It was associated with the formation of stiff continuous network of cellulose link through hydrogen bonding with the surrounding molecules. And the surface properties and the interior of the film were also characterized by using AFM and SEM respectively. And the conclusion of this chapter are novel composite coating formulation using 0.8% of chitosan, 0.5% essential oil, and 0.25% cellulose were developed, and the incorporation of cellulose as a stabilizer agent into the chitosan and essential oil Pickering emulsion coating was found to improve the performance of antifungal activity synergistically, confirmed with in vitro and vivo assays. And the addition of cellulose nanofiber had potential to improve the functional properties such as light transmission and UV and visible light wavelengths and tensile strength. And the general conclusion from this presentation are the combination of chitosan and Indonesia origin essential oil and nanoparticle, both organic and inorganic, affected the physicochemical characteristic of chitosan base coating. And this combination approach could become an alternative antifungal fruit coating, which was confirmed by in vitro and vivo assays against Penicillium italicum, Penicillium digitatum, and Botrytis cinerea. The future works that the additional investigation are needed, particularly for physicochemical characteristic and sensory acceptability, to confirm the potential of this novel active coating in maintaining the quality of fresh fruit commodities. And the additional research development should focus on improvement to the technology transformation from the laboratory scale to a commercial scale process using a continuous coating and casting equipment. Thank you very much for Professor Takashi Okayasu and Associate Professor Yasumaru Hirai for reviewing my PhD thesis. And also I would like to thanks to Japan International Cooperation Agency through the Innovative Asia Scholarship Scheme. Thank you very much for your attention. Arigatou gozaimasu.